Hi everyone, we're continuing with Taylor series and we're talking about really what they're useful for, which is approximating functions. Right, so similar to Taylor polynomials, except this time with a series. They're really good for approximating especially like transcendental functions that seem kind of arbitrary to us. Like for instance, sine. Okay, sine doesn't work well for numbers not on the unit circle or zero. If you try to plug 1 into this, for instance, it gets you really weird numbers and difficult to work with, except we can approximate it using a polynomial, and we can plug 1 into this polynomial, and that makes much more sense to us. So we can actually get values for sine by using the Taylor series or the Taylor polynomial, and it's much easier. You can actually do that without your calculator. All right, so first thing we're going to do is use the Maclaurin series for sine to approximate sine of 1. Okay, so I'm going to write down our Maclaurin series that we talked about. It's x to the 2n plus 1 over 2n plus 1 factorial. And now they're asking us to approximate sine of 1, so I'm going to go ahead and substitute 1 in for x. Okay, well, 1 to any power is always going to be 1, so I'm not really going to worry about this, and I'm going to write out a couple terms. Right, so my first term is 1 minus 1 over 3 factorial plus 1 over 5 factorial, and it asks us to stop when our error is less than 1 over 1000. All right, so I'm actually going to stop here. The reason why is because I know that my error is the next term. So my error is bounded by 1 over 7 factorial, which is actually less than 1000. All right, it's about one. I think it's about 1 over 5,000. Okay, 7 factorial is almost 5,000. It's a little over 5,000, I think. All right, so that is definitely less than 1 over 1,000. So this is what my approximation is. Now, if you use your calculator to find the actual error, right? So 1 minus 1 over 3 factorial plus 1 over 5 factorial is 0.8416. Okay, I'm truncating after 4 decimals here. Now, if you find sine of 1, it's 0.8414, right? So even just using 3 terms, I got a pretty dang good approximation. Yeah, my error came out to be about 1 out of 5,000, okay, 1/5000th of an error, which is, honestly, because we truncate after 3 decimals, you wouldn't even notice the error in this situation. Right, so with just 3 terms, we got a pretty good estimate. And this you could totally do without your calculator. Now, 5 factorial is no small number, but it's still possible to do this without your calculator, as opposed to just doing sine of 1. I don't know, it's a lot more arbitrary to me. Okay, now we're going to do the same thing, except an integral and sine of x squared, a little more complicated. All right, so in our previous notes, we actually already got a Taylor series for sine of x squared. So I'm going to write out what we found last time. All right, so we already did this on our notes last time. Now I'm going to write out my integral. That's t squared. All right, and so if I integrate my general term here, okay, very similar to what we've already done in our notes. Okay, I'm going to increase my power by 1 and divide by my new power. All right, so let's write out some terms. So I am trying to approximate the integral of sine of x squared from 0 to 1. Right, now that is exactly equivalent to my Taylor series that I just found. Except I'm going to plug 1 in for x. All right, so I don't really have to worry about this because 1 to any power is 1. I'm going to write out my terms. This is going to be approximate. So now here's my estimate. 1/3 is my first term. 1 over 7 times 3 factorial is my second term. And again, I'm actually going to stop there, right? Because my next term is going to end up being 1 over 11 times 5 factorial, which is less than 1000. Okay, now we're asked to use our calculator to find our actual error, and again, we get pretty close. Right, so I'm going to scroll down. And so 1/3 minus 1 over 7 times 3 factorial. Right, it's two terms. It's just two terms. I get 0.3095. Okay, the integral from 0 to 1 of sine of x squared dx is 0.3102. Right, that gives me an error of 0.0007. That's a very small error, and that's only two terms. Okay, to me that's a pretty dang good approximation. All right, so my error was, again, pretty small. All right, last thing, and this is pretty cool. All right, so first we're going to write out our Maclaurin series for e to the x, which hopefully we know. Okay, this one's pretty simple. Oops. All right, that's the first four non-zero terms, and then my general term. Okay, so here's my Maclaurin series for e to the x. Now they want me to use this to find my limit here. The limit is 0 as x approaches 0 of f of x minus 1 over 2 to the x, where f of x is e to the x. Okay, now, yeah, I'm actually going to show you this three ways. Okay, first way, something you already know. Okay, I'm plugging in e to the x here. So limit x approaches 0, e to the x minus 1 over 2x. Okay, if I plug 0 in, I get 1 minus 1 over 0, which is 0 over 0. That means I use L'Hopital's rule. E to the x over 2, I plug 0 in, I get 1/2. Okay, so this is something that you already know how to do. Let's do it again, except this time, let's use our Maclaurin series. Okay, so limit x approaches 0, I'm going to plug in 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Okay, minus 1 divided by 2x. Okay, well, these will cancel. I plug 0 in, I get 0 over 0, which means that, hey, I can use L'Hopital's rule again. So if I use L'Hopital's rule, now let's take the derivative of my Maclaurin series here. The derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 factorial. Well, this is the same thing as just x squared over 2. The derivative of that, well, the 2 drops down, which is just x, so I get x here. Now here, so the derivative of x cubed over 3 factorial. Okay, well, that'll be 3x squared over 3 factorial, but, well, this is the same thing as 3 times 2 times 1, so the 3's will cancel, and so I have x squared over 2 factorial. Oh, okay. Oh, hey, look at that. And the pattern keeps going. So notice how I took the derivative of my Maclaurin series and I got the exact same thing back, which, as you know, the derivative of e to the x is e to the x, so its series should work the same. And it does. And now if I plug 0 in for x, all these terms go away. I end up with just 1/2, my two constants. All right, one last way. Let's do it again. Okay, I'm going to plug in again. I'm getting lazier with these, huh? All right, I'm once again going to plug in my series. All right, subtracting 1, dividing by 2x. Okay, so the 1's go away. Now I'm going to divide each term by 2x. Okay, I'm not going to take the derivative or anything. I'm just going to divide. So x over 2x is 1/2. X squared over 2 factorial divided by 2x is going to be x over, 2 times 2 factorial. This is going to be x squared over 2 times 3 factorial, yada yada yada. When I plug 0 in for x, all these terms go away. I'm just left with 1/2. It has three ways of evaluating the same limit. Right? Two of them using a series and one of them involving taking the derivative. I think the cool thing is that the derivative remains the same no matter how many times you differentiate. All right, that's it for this. I'll see you all later.